welcome to this video. Today is a little bit of a different video. I have my iPad here and I also have my pencil, and we are going to be doing some thermochemistry review. I'm going to start by going through a few definitions, words you need to know, words all need to know. Obviously, you don't have to watch this to learn. But yeah, I decided to make this video because I needed to study, and I enjoy watching things that I don't understand to fall asleep. So anyways, afterwards after all my examples and definitions, I'll do some real examples that I have not done yet. So let's begin. So thermochemistry introduction. What is thermochemistry? Thermochemistry is the study of energy changes that accompany changes in matter. So we have physical changes. So physical changes are substance, where the substance changes appearance, but not identity. So for example, we have H2O in the form of ice, and as it melts, it's going into water, into its liquid form, but it's still staying as H2O. So the chemical compound is not changing, just the appearance of it. Then we have a chemical change, so that is where the compound does change, and there's a production of a new substance with new properties, so any chemical reaction. Then we have nuclear, which we're not really going to touch on, but it's still good to know. And nuclear forms new products by changing the nucleus of the atom. And I don't know if I'm correct, but I think it's something where it's the atoms fuse together. I don't know. I think we didn't touch too much on that, but I learned a little bit about it in one of my other classes. So then we have energy. So energy is the ability to do work. Work is movement against resistance. So even me just moving my hand, I am battling the resistance of the air that is pushing me this way, but I'm trying to go this way. Even my pen being dragged along, the friction is trying to pull me back, but obviously it's not very it's a very smooth surface, so there's not much friction. But if you were to go on a very rough surface, it's much more difficult to move, so that's where it gets more difficult, but that's more physics. So anyways, energy is just the ability to do work, so just something moving. Well, kinetic energy is a type of movement, but there's a few different types. So the unit of energy is joules. This is a joule, but in thermochemistry, we also use a calorie. So 1 calorie is equal to 4.184 joules, and this is basically the specific heat capacity of water. So 1 calorie is the energy required to raise 1 gram of water by 1 degree Celsius, which essentially is just heat capacity, but we'll get into that. I'll further explain that. And then we have potential energy. The potential energy stored in bonded atoms and released during a chemical reaction. So chemical energy, the potential energy stored in bonded atoms, and then it's released later on in the chemical reaction. But what does potential energy mean? Well, this is obviously in terms of atoms, but let me show you how I like to explain it. So let's say we have a cliff here. This is our cliff. This is the top of our cliff right here, and then this right here is the bottom. So let's say I place you right above here. Right now, you have the potential to fall all the way down. So that's a lot of energy, the potential energy that you store right there in that moment. Versus if I put you right here, well, if I pull the ground out from under you, you're not going anywhere because you're already on the ground. So you have no potential energy. In terms of physics, the actual formula for potential energy, so this just means potential energy or energy potential, is mgh. So we have mass, gravity, and height. So if your height is up here, let's call this 2. And we have 2h. If it's down here, it's 0. But here's the thing. If any one of these, if our mass, gravity, or height is 0, then there is no potential energy, right? Because you can't multiply something by 0. But that's more just to understand what potential energy is. Okay. We have the reactant, so the input required energy to break the bonds, and then the product is the energy released when new bonds form. We have exothermic and endothermic, but I don't really like this an analogy, so I'll go through that later. The next thing that we have is thermal energy versus temperature. So these are two very different things. Thermal energy is the sum of kinetic energy. A bigger object has more thermal energy. This cannot be measured. I will go into what this means. And then the temperature is the measure of average kinetic energy in the molecules in a substance. This can be measured using a thermometer. So this is my favorite example. Is we have a nice iceberg here, and I'm just gonna redraw it. But this is an iceberg, and the iceberg is obviously a lot bigger than a small ice cube, right? That's obviously a lot bigger. So which one has more thermal energy? Well, this iceberg. Why? Because, well, it's a bigger object, but that's not the reason. Let's say we put this ice cube into a pot of water. This is our pot right here. Obviously this iceberg's not going to fit in the pot of water, but let's say we're boiling this pot of water, so it is getting hot. Let's use the same amount of water for this iceberg to melt this iceberg. Which one is going to melt faster? Well, obviously the ice cube, because it's smaller, it has less kinetic energy. This one has more kinetic energy. And what I mean by kinetic energy is within any substance there is molecules within. There's molecules, right? So depending on what the substance is, so for example an iceberg, the molecules there'll be many molecules obviously, but they'll be like vibrating or rotating. They won't be moving. The more a molecule can move around, the more heat the substance has, so the more like liquidy it will be, right? Right now we're in the solid form, so we can't really move our molecules, but let's say we can fit about 3 molecules here. Obviously it's a lot more than 3, but just for this example, this molecule or this substance, we can fit many hundreds. So the bigger object has more thermal energy because the sum of the kinetic energy is higher, because there's more molecules within this, so it's just a greater space versus this one's smaller, right? Temperature is the measure of average kinetic energy of the molecules. So in this one we have less molecules, so we have less molecules, so our average will be between just these 3 molecules, versus here it'll be between these hundreds molecules. So it'll differentiate like that. But okay, I've explained it better before, but anyways, let's go into thermometers, how they work. It's very simple. I'm not going to go too detailed into it, but thermometers essentially are placed into a substance, and in the substance, as I said, there's always molecules moving around, right? And so the molecules are either going to be moving slowly, or they're going to be moving very fast. And when they're moving fast, that means that it's a high temperature. Anyways, if they're moving slowly, as they hit the thermometer, well, it is going to take energy from the thermometer, which is this red part right here, and it'll drop. It'll drop, which means the molecule is moving slow, meaning that it's a colder substance. If it's moving fast, well, as soon as it bumps into this, it's going to spike the energy. It's going to spike the red little line, right? So that's saying that it's hot. Anyways, that's just something simple, but a simple explanation. I don't know if that's perfect. Okay, we have some definitions here. I don't want to go through all of them. I will go through the important ones. So we have surroundings. Surroundings is all the matter that is not a part of the system. Well, that's not really a great definition, but the surroundings is basically yeah, anything that's not the system. Let's just explain what system is first. So a system is basically whatever we're observing in a within a experiment. So in an experiment, we're observing the reaction of the chemical reaction. The things we're not observing are the surroundings. So the cup, the water, that's not included, like anything that's just not included, the air, like usually we don't take into effect the air at this level, but the cup and the water is very important, but those are the surroundings. So there's a few types of systems. So we have open systems. So this can exchange both energy and matter with the surroundings. And then we have closed systems, which can exchange energy but not matter with its surroundings. So I like to think of it like a door. We have a open, let's say this is a wall. This is our open door right here, right? This is our open door. The molecules can come and go freely as they wish. Their energy, their matter, everything, they can go. They have no issues. So that's because the door is open. In a closed door, the molecules, they can knock on the door, right? And those that knock, you can still hear it from the other side. So the energy is still there, but the molecule itself will just bounce back. It cannot make it through the door, right? You can't go through the door if it's closed. So that's just how I like to think of open and closed systems. And then we have isolated systems. So this is where neither energy or matter can move in or out of the system. This is theoretical because I don't think it's theoretical, but it's impossible to set up a true isolated system on Earth. And then lastly, the few things here is exothermic and endothermic. So exothermic is releasing energy to the surroundings. I like to think of endothermic and exothermic in terms of the surroundings, so in terms of the cup and the water. So if a reaction is exothermic, then that means that the cup or the surroundings are gaining heat, meaning if you touch the cup, it's going to be very hot. So when the surroundings are positive or gaining heat, it's because it's taking it from the system, versus if the system is positive or gaining heat, it's because it's taking it from the cup, which is endothermic. So it's absorbing energy from the surroundings. So if we're using the same example of a cup, you feel the cup and all of a sudden it starts to get cold. Well, that's because of the actual reaction taking place. The system is gaining that energy, gaining that heat. Okay. Fusion and fission. So, okay. Yeah, so fusion is the process of combining two or more nuclei. Okay. And then, okay, fission is splitting a nucleus. So fusion is adding, fission is splitting. Okay. So we have a few things here. Did I do specific heat capacity? I don't think so, not yet. Okay. So what is affecting the heat of a substance? We have the mass, we have the temperature change, and then we have the type of substance. So the mass affects the how an object gains energy or loses energy. Of course, as with the iceberg example, the mass, this one is going to melt much slower than this little ice cube right here, right? So the mass is definitely taken into consideration when affecting heat. We have the temperature change. So the more temperature increase, the more heat is required, which is pretty self-explanatory. Then we have the type of substance. So each substance differs in ability to absorb heat. This is known as specific heat capacity, which is what I'll get into here. So the ability of a substance to resist changes in temperature. So heat capacity, the actual definition is the amount of energy required to change the temperature, change 1 gram of a substance by 1 degree Celsius. So things like metal have a, oh man, is it higher? No, because if you have a higher, so things like metal will have a lower heat capacity because they just have more ability to just within the molecules themselves, they tend to, okay, hold on. So metal has less. Okay, this is where I need to do some researching here, but I'm gonna do that after. Just make a little note here, just to confirm my test is tomorrow. But so metal has lower heat capacity, and which makes sense. Well, if it's true, like, hold on. That's why they use metal mugs to keep stuff warm, because it's good at insulating. Okay. And then molar heat capacity is basically the same thing, but it's to raise 1 mole of a substance by 1 degree Celsius. Okay. So what is affecting heat capacity? So what affects heat capacity is the intermolecular forces in the states, the size, the number of bonds, and then the type and strength of the bonds. So that's what it is. Metals have very strong bonds, and so that's why their heat capacity is higher or lower. I need to think here because water is quite high, but aluminum is lower. So I think it is lower. I'm pretty sure it is lower. I can do a quick research here on my computer. And I'll just search up if metal has lower capacity. Yeah, they have lower heat capacities because compared to other materials like water, as I mentioned, because they require less energy to raise their temperatures. And this is because, yes, of their close-packed atomic structure, which transfers thermal energy efficiently. Right. Okay. Yeah. I don't know what that was. Oops. Okay. Okay. So that's what's impacting the fact that they have a closer atomic structure. They're packed closer. They're very dense compared to water, which has free move or not. Like the molecules are moving throughout. Okay. So how is energy transferred? We have heat. This is the molecule, so it can move translationally. This means that it's moving throughout the substance. We can have vibrational or rotational, which is what I mentioned above in the iceberg example. This would be in like a solid kind of substance. So the solid substance is where the molecules are not moving, does not increase the temperature. And then the translational ones where it's moving throughout does increase that temperature. Yeah. Okay. So we have a few. This is, by the way, our basic equation just for calculating quantities of heat. We have mass, specific heat capacity, and then the delta T, which is the change in temperature, which is all the things that we mentioned in what affects heat. So it's very simple. It's a very plug-in equation. So 600 grams of water, we have 20 degrees Celsius to 85 degrees Celsius, how much heat flows into the water. And then the specific heat capacity is given to you, or you have to solve for it, but you have to be given another value. Yeah, so we have, okay. So from this example, we have a 163 kilojoules. This means that heat is positive, like heat was gained from the surroundings. So it's an endothermic reaction because the system itself is positive. So that's the difficulty with thinking in terms of systems and surroundings. You want to make sure that you know which ones you have to think in terms of, because here you have to think in terms of the system. Well, the system's positive, so then that means that it's endothermic, versus if you're thinking in the way I explained it before, exothermic and endothermic. I was thinking in terms of the surroundings, where if the surroundings are positive, then it's exothermic, but this one is not. Okay, we have heat transfer. So heat transfer basically just relies on the conservation of heat, or conservation of energy, sorry, where no energy can be gained or lost. So that just means Q equals MCT. So MCT is equal to MCT. The final temperature will be the same for both, like substances or objects, because of the conservation of energy, right? So nothing's gained or lost. Okay, we have to do some enthalpy of physical changes. So total enthalpy of physical changes is total energy of the system. It's always calculated as enthalpy change, so that is delta H. And then what does this say? When container is open to surroundings. Okay, all right. Okay. Okay. So, let's do. Let's do state. Okay. No, we'll do this. I don't really like the way this is all organized, but let's do endothermic and exothermic graphs, which I have down here. Actually, I have some right here. Okay, so exothermic is also in terms of the system. So the way you have to memorize, the way I remember the definitions of exothermic and endothermic is in terms of the surroundings, but when you're doing the actual processes of determining an exothermic or endothermic reaction, you need to look in terms of the system. So this is in this graph is of the system, right? So we have our reactants, and then our products are at a lower enthalpy. And yeah, like the way that you are going to find this is just by determining if a reaction is endothermic or exothermic, like which I just did with this one, this Q up there. So Q was positive, so it's an exothermic graph. So it's oh my, what am I saying? Q, I don't know if this is right. Heat was gained from surroundings. The system is negative. It's endothermic. No. Okay, let's see here. We have exothermic. No, sorry. Yes. Yeah, this would not be exothermic. Well, if heat is gained from the surroundings, then it should be. Okay, I don't know. This note is confusing. It's been quite a while since I've looked at these notes, but okay. Yeah, so we have anyways, endothermic. So our system is gaining heat, which means our surroundings are losing heat, so the cup is becoming colder. And then exothermic, our system is losing heat, the cup is becoming warmer, and it's negative, right? So that's why I just don't understand, because if that was exothermic, the one up there, then it would be negative. Okay. Molar enthalpy of combustion. This is not bad, but I'm gonna go down here because I did it over here, and I just want to do it over here. Okay, so molar enthalpy of combustion basically, all it is just this equation. So the enthalpy of combustion is equal to the moles of the enthalpy of, I think, the formation of combustion. I don't know. They're different though. So it's very simple. We're given a mass, and then we're given this one, and so we wanted to find this one. So we have the mass of methane. So methane is CH4. So we can find the molar mass of this, use this mass to find the N value, and then we can just times it in order to find our enthalpy of combustion. Okay, so that's molar enthalpy of combustion. Okay. So the next one is calorimetry. So calorimetry is the science of measuring the change in heat of a chemical reaction or physical change. So a calorimeter is just an insulated reaction vessel in which a reaction or physical process can occur. So as I was saying before, we had that cup, the styrofoam cup, that can be used as an insulator. We have a, okay. So the change in temperature of the surroundings can be measured. So for example, the water, in which is the solution, not the reaction, can be measured. The change in temperature in that can be measured using a thermometer. But the system itself, so the reaction itself, cannot be monitored. And the reason it cannot be monitored is because we can't like physically determine like the breaking of bonds and stuff, because that's what it is, right? The system is the breaking, the bonds breaking or forming. Like we can't monitor that, and so the amount of heat released or absorbed can be calculated, so of the surroundings. And then we have so basically calorimetry, you want to get the heat of the surroundings, and then where's my nice equation? It's delta H is equal to negative Q surroundings over N. So to find the enthalpy of the reaction is just taking the negative of the heat of the surroundings over the moles of the product, or not the product, the system that you're looking for. If you have a system where you have two or more compounds, you need to look for the limiting reagent, the one that gets used up the fastest. Okay, so this cannot be used for reactions involving gas and cannot be used for high temperature reactions. So why is that? Why? I don't know. So why can calorimetry not be used for reactions involving gas? I don't know. That's something I'm going to search up. Why can calorimetry for gases? Oh, that makes sense. It's going to be very difficult. Because the gases are flowing out, of course. High temperatures, I assume it's the same thing. Or material failure, significant heat loss. Just inaccurate. Okay. That makes sense. Okay. So we have some problems here, and I'll just go through it, and then I do think I have a calorimetry. Yes, I do. I definitely do. Okay, so a chemist wants to determine empirically the enthalpy change for the following reaction. So we want to find delta H of this reaction. This is now our system. He uses a coffee cup calorimeter, blah, 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 blah. We're given all the values essentially in this paragraph. So that's what I did. I wrote out our givens. Actually, I did not. Okay, anyways. so we have our T1 and our T2, 20.4 degrees Celsius and 40.7. So our delta T is going to be 20.3 degrees Celsius. The next thing I like to do, I don't like the way I laid out this question, but I like to go through and label what is our system and what is our surroundings. So I did it kind of here. This is our system. This entire reaction is our system. That's what we're trying to observe. And then these are all part of our surroundings. So the thing here is, I think we have the solution, and then 0.5 HCl 0.5. So okay. So in terms of the solution, we are adding our Mg and our HCl, which I put just 100. It should be 100.5, which doesn't make a huge difference, but anyways. And then we have our specific heat capacity and our temperature. We are only given, one here. Okay, anyways. And then we have our negative. Okay, yes. Okay, it doesn't look like I finished this question, but okay, we're given our negative Q here. I guess I'll finish it. So now we have our Q. We want to find delta H of the system. So we can have negative Q over N. Now the issue here is that we have two products. We have our, to determine which ones are moles, we have our HCl, and then we also have our Mg. So which one do we use? Well, we use the one with the smallest moles, so that's finding the limiting reagent. The reason that we use the one with the smallest moles is because if we were to use the one with the largest moles, then that just wouldn't work because, well, this is kind of difficult to explain, but how do I explain it? Okay, we have this amount of Mg. We have this amount of HCl. If I am to use all of this, if I want to do these, put these in equal amounts, I need to be sure that my Mg goes in first because it's less, right? And then that means that I will be left over, yes, with some HCl, a little bit of HCl, right? That's the best way I can explain it, but anyways, so we have, I think it was negative 8.5, negative 8.5 kilojoules, and we want to find our limiting reagent, so let's do that first. So for HCl, am I given? Yes, I'm given the equation too. So for HCl, we have 100 grams, I believe, and it's mass over molar mass. So the molar mass of HCl, is where I grab my periodic table of HCl. We have 1.01 plus 35.45, so we have about 36.46, I guess. I need to do calculations for the easiest stuff, but okay, just to make sure. Anyways, so let's find the moles of that. So 100 divided by 36.46. So we have 2.7 moles of HCl. And then let's do Mg as well. So Mg, it was 0.5 grams. And this is grams per mole, so it'll cancel out. And the Mg is 24.31. So we get 0.5 divided by 24.31, 0.02. So right now, this is looking like our limiting reagent, but we have to check our reaction first because we have to look at the moles, because this has 2 moles versus this has 1 mole. So we want to find, we need Mg, we need to find them in terms of whatever. if we can do whichever, it doesn't matter. Let's do HCl times, we'll put HCl at the top, so 2 moles of HCl to 1 mole of Mg. Because right now these are in different combinations, right? It's hard to explain. You have to take chemistry. I don't know. This is like... anyways, we're going to get something way higher than that. So obviously this one's our limiting reagent. So we are going to be using the moles for this. So we'll have 0.50 grams over 24.31 G per mole. So let's do it. Let's see what we get. 8.5. We get negative 413.27. Sig figs do matter. I absolutely hate sig figs, but they do matter. So I don't know. Okay, I'm gonna just check the answer here. Okay, I did not. So, okay. So, this is calorimetry. Really any answers. Okay, I just want to make sure that I have this correct. Okay. I don't know. This might be correct. So right now we have kilojoules per mole. Okay. That is that in terms of that. We need to... This is the enthalpy of the system. Oh, I see. I think we need to times it by... something. But why am I not understanding? We need to do... Okay. This is kind of annoying to do. So we have the system. We have this, which we just got from that. The Q, this is in terms of Mg. This is in terms of the moles of Mg. Mg has 1 mole, this has 2 moles. Like, we need to multiply by some molar value, but I don't know what. Okay, let me see if I can find this online. Oh, it says it's in form Mg. Okay, I see. But I'm just gonna do one extra thing because there's something else I'm looking for where it's where we are left with kilojoules, just kilojoules. So let's just check if this answer is right. Yes, it is. Okay. Not my sig figs though. So should be, I mean, it should be 3 sig figs. My answer is a little bit off, but it's because I just didn't use much approximation. I mean, I used too much approximation. Okay. So this is what I'm confused about. What would the enthalpy be for the entire reaction? Or it is this, because mg is the entire reaction, but how do I get it in just kilojoules? Oh, nope. Oh, wait. This is, it's negative, okay, right. Wait. Okay. So this is molar enthalpy. That's what, okay. If we wanted just to find the change in enthalpy, that would be just this, which is Q surroundings is equal to negative Q system. So it would be negative 8 point. Okay, so it would be, this is our enthalpy change. Technically, kind of, okay. So it would be an exothermic reaction because we have a negative thermic, because our system is losing heat. And what would that look like on a graph? Is heat when this doesn't make a line is something like this. So we'll have our reactants. And then it's losing heat, and then our final product's something like this. And H is negative. So this is exothermic reaction. Yeah. Okay. Excellent. So that's kind of that one. That one took me a while, but just a few mix-ups. Okay. We have, okay, the next one I want to do is some physical change ones. So these are a little bit confusing, but not really. You need to just know the graph and how to do the graph. So I did do the graph over here. So we have for heating, we're reading it from left to right, of course. So to heat, we have, this is our ice here. We melt it to 0 degrees right here. This is at 100 degrees. And yeah, and so anyways, we have melting, we have vaporizing. So these each have a different enthalpy. And it is actually the same enthalpy as our cooling one, except for our cooling one will have a negative enthalpy. The negative version, sorry, not negative. Well, yes. So here should be negative, yes, because we're going down. Okay. So the enthalpy, yes, of steam is this, except we are not doing vaporization, so that's where I messed up on this one. But okay, so yeah, you just have to memorize these kind of words, I guess. We have condensing and then freezing. So condensation is from gas to liquid, freezing is liquid to solid. We have melting, so that's from a solid to a liquid, and then vaporizing, so a liquid to a gas. And yeah, that's actually not that difficult. But okay, so essentially what we have here, I did a diagram that I liked. No. Let's see. I did do a diagram where I kind of, okay. Anyways, I'll just explain it to you. I don't know where my diagram is. So basically we have these on our graph, we can see we have these slopes going down or going up, whichever graph you're looking on. And then we also have these increments where, or not increments, we have these locations where we have just a flat slope. And what this is basically the energy going towards breaking and forming new bonds, so to change the state. The energy is going towards oh my god, no, I had a perfect like I wrote the exact same down on another one, exact same thing down on another one. That's annoying. I don't know where it went. I'm just not looking hard enough, I guess. Okay. We oh, right here. Okay, so this flat part is going, the energy is going towards breaking the bonds. And then the energy as we move up or down is the energy towards changing the temperature. So the energy can only go towards so much, right? So anyways, that's just what the flat and slope parts mean. The flat part of the graph, I'm pretty sure the energy goes towards breaking and forming new bonds, but let me double check. So energy in the flat part of a physical change graph is the energy going toward breaking and so the energy, okay, so we have the energy of a flat part of a physical change graph is one of those. Okay, so in a heating graph, oh, I see. Okay, in a heating graph, so this one's a heating graph. Energy. Wait, what? Oh, I see. Okay, so in a heating graph, the energy is going towards breaking bonds or weaken forces. Oh my god, sorry. Or weaken IMFs. And then in a cooling graph, okay, so these are actually different. Okay, it makes sense. In a cooling graph, so one where we have down, where we have these ones here, it's energy. Energy is going towards only being released as bond forms. Energy is only being released as bond forms. Yeah. So you're not rearranging atoms, of course, because you're not making a new substance. You're just changing how the existing molecules are close to each other. Solid going down. Energy is released as intermolecular forces form. Oh, what? The plateau. That's what I'm wondering about. Wait, what? Okay, confused. I'm gonna search something different up. Releasing, breaking. Okay. So, okay. Melting or boiling? Melting or boiling. Breaking forces. But that's not the flat parts. No, yes it is. No, it's not. So the rising parts, yeah, are changes in temperature, so increasing kinetic energy. Okay, I see. So it is these forming. IMFs. Okay. So these are breaking, forming intermolecular forces, which, if this, what I'm understanding basically, because we have forming more forces makes the substance like more durable. Yeah. So there's more forces, so that's why it's becoming more close and okay. That makes sense. Okay. Okay. So I think the next part actually, let's do some Hess's law and then standard enthalpy of formation as well. So, which I believe is this. I enjoy Hess's law. I do. I don't really enjoy this one. This standard enthalpy of formation, but we're gonna have to do it anyways. So, okay. So standard enthalpy of formation is essentially just following this. Which I had it bigger here. This formula. We have the enthalpy of formation is equal to the sum of moles of the enthalpy of formation of the products minus the sum of the moles of enthalpy of formation the reactants. So PR. Do not get them mixed up. PR. It's PR, not RP. So first things you want to do is gather your givens. So in this question, well, I don't have the question written down. We have our givens, and I guess we have this, and you need to make your equation. You need to balance your equation, all that good stuff. And then you should be given your enthalpies of formation. That should be given to you. One thing I will say is the enthalpy of formation for anything like O2, N2, any element on its own is 0. And it's 0 because it requires no energy to form. Because that's just its natural state, versus H2O, well, that's going to require some energy to form, and so that makes sense. Okay. So, excuse me. So, okay, the first thing you need to do, make your equation, and then it's just a matter of plugging in numbers. Yeah, I would say take your time with it because it takes a while, but so in the equation, the moles are the moles from the equation. So we have 2, we have C2, and then we have 7, but that doesn't really, 7 over 2, sorry, but that doesn't matter because we have 0, right? Because that already exists in its natural state, and then we have 1 here, but that's nothing, right? So we have negative 1512.4 minus negative 84.4 kilojoules. And so we're left negative 1428 kilojoules per 1 mole of C2H6. But in this question, I think we were asked to find it in terms of H2O for 8.65 grams of H2O. So we want to find, we want to basically convert this into per moles of H2O. Per first 8.65 grams of H2O, which we can do by finding the moles of H2O. So we get 0.8480 moles of H2O times 1/3, because we have it already in terms of C2H6. So we do 1/3, it's 3 moles H2O, 1 mole C2H6. We get the amount of moles in H26 times that, bam, we get it. I'm gonna go over some of these on my own time. So I'm just gonna put a little star here because it's very easy, but it's gonna be hard if you don't already, you're not good at it, right? So, okay. The last thing I will go through, and then I'll do my examples, is Hess's law. So Hess's law is very simple. It was very difficult to me trying to learn it on my own, but as soon as I had someone explain it to me, it's very easy. You want to follow these 7 steps. These steps are very important. Number 1, balance. 2, examine and compare to target. 3, reverse equation. 4, multiply coefficients and enthalpy. 5, stack equations. And then 6, cancel what's on both sides. 7, add what remains. So we want to find the enthalpy. Basically what this is asking is find enthalpy of this equation right here. So this one right here, that is what we're looking for. This is our target. So what are some elements that we have in our target? We have CHCl3, we have HCl, we have CH4, and we have Cl2. So using all of these equations given, we want to find which ones are in there. Okay, we don't have H2. I'll leave it for now. We have Cl2, I'll underline that. We have HCl, I'll underline that. We don't have C, we don't have H2 again. We do have CH4. No C again, no H2. We do have another Cl2, and we do have CHCl3. So now we need to examine which ones are on the right side. So according to this target, we should have as our reactants CHCl3 and HCl. CHCl3 right here says a product, so that's not going to work. We need to flip this equation. So that means our Cl2 is now going to become a product, so is our H2, so is our C. And when we do a flipping of equation, we need to flip the sign of the enthalpy as well. So here, now we have CHCl3, and it goes into CH2Cl2, and we have a positive 1,178 kilojoules. Same thing as number 1 over here, we need to flip this. So we're going to flip this entire equation, flip this sign, and bam. Okay, so now we are left with what we have here. We have HCl3, and we have Cl, or 1/2 Cl2. In our needed equation, we have 3 HCl, so that is going to be not enough, right? We only have 1 HCl, 1 mole of HCl. We need 3 moles, so we're just going to multiply the entire thing by 3. By multiplying the entire thing by 3, we have 3 HCl. We have whatever 3/2 H2 plus 3/2 Cl2, and then we multiply this as well by 3, so we get 184.6 kilojoules, which does not seem right because that's not times 3. Hold on a minute. 92.3 times 3 is not 184. Okay, it should be 276.9 kilojoules. That looked like it was times by 2, but okay. Let's check our other ones. So our CHCl3, it has 1 mole, 1 mole, we're good. Cl2, so we have 3 moles here. We have 3/2. We also have another 3/2. So by adding these two, we are left with 3 Cl2. So that's fine. These are fine. Okay, so now our next step, we did that. We now have our equations stacked. I know it's a little bit messy, but now we can cancel what's on both sides. So if we have a C on our reactant side, we also have a C on our product side, so those can cross out. H2 on product side, H2 on reactant side, we can cross out, except that this one is 2. This one's only 1/2. So we still have 1 mole of H2 left, but we still cancels out. Oh, because I have 3/2 here. That's why. 3/2. So yes, we are left with 0. But yeah, add these together, it makes 2. That's why. Okay, we're left with. So then we are left with now 3HCl, CHCl3, Cl2Cl2, right? Because if we're adding these, and CH4. Okay, and then now we add all of these separate enthalpies, which, let's see here, 0.9 plus 1178 minus 74.8. So 1.38, which I guess I got 1.28, which makes sense because I did only by 2. Okay, so that's it. That's essentially just Hess's law. Very simple. I enjoy it. Okay, now let's do. Excuse me. Let's do some questions here. So I have 2. Okay, one of them was Hess's laws, and then one of them is just finding the enthalpy of a system. Okay, so Hess's law. We're gonna go over the same thing. So we need to find this using these 3 equations. Okay, first thing I like to do, let's see which ones we have. So we have N2H4, H2, NH3. N2H4, yes. No N2, yes, H2. We have Na2NH3. We don't have N2, we do have H2. And then we have H2. And none of these. Okay. Which ones are on the wrong side? This one's not on the wrong side. This one's not on the right side. This one is on the right side. This one's not on the right side. Okay. So the next thing that we want to do is I can already tell what to do here by kind of looking at it. This is a very simple problem, but essentially we can kind of skip steps here and we can just cross out what we don't want. So I don't want, as long as I'm not gonna move around my equations, right? I don't want this and I don't want this. I know they're in my equation, but if I flip this, then my N2H4 is not on the right side, so I'm just gonna get rid of it. Those are now crossed out. My N2 and my NH3 are fine. This one is the only one I'm going to flip, so I'm just going to flip this one right here. So by flipping, we're going to get H2 gas plus CH2OG yields CH4O liquid. And then our enthalpy is also going to be flipped. So 65, going to be positive 65. Okay, now we need to make sure that our moles are correct. So we have H2 is fine because we only have 1. N2H4 good. This one also good. So excellent. There's no need to multiply any of the equations. Now we can just cross out what we have on both sides. We have this on 1, this on 1. We have CH4. Okay. So now I have rewritten this equation so that the H2 is in the same reactant spot as the other one. So I'm just gonna cross off this equation just to make it easier to read. So now what I can do is I can cross off products that are on both sides, products that aren't needed, and they're on both sides. So, by the way, when you cross off stuff, it has to be the same state form. So this is a gas, this is a gas. I can cross these off. N2 is a gas, N2 over here is a gas. I can cross that off. CH4 is a liquid, CH4 is a liquid. Cross that off. They also have to be on separate sides, so reactant and product. But okay, so now I have, I think, crossed off everything that I need to. Anything that's not in the equation, basically. And now I can rewrite my equation. So I have N2H4 up here. N2H4 liquid plus, what else do I have? I have H2. That's a gas, and that gives us 2NH3. And that's a gas. And so now we're going to add up all of these enthalpies. So let's see what we get. Negative 37 minus 46 plus 65. Good. Enthalpy of negative 18 kilojoules. And just to check, yes, that is correct. Okay. So the last one I'm gonna do before I do work on my own is finding the enthalpy of a system. So here I am given a set of values and I'm given an equation here. So as soon as you can see an equation, you can kind of just assume that this will be the system, and all of our values will be calculated as surroundings. So we have a bunch of different specific heat capacities. So what this is basically telling us is that we are going to have a few different surroundings to take note of. So our Q surroundings, to find the surroundings of more than one surroundings, it's just going to be Q1 plus Q2 ... like plus plus plus. So the first one that I can kind of note is the one we have the solution. So that is going to be the solution, and our Q is going to be MC delta T. The other one I can note is the cup. Cup, again, it's going to be Q equals MC delta T. And then the last one is going to be the thermometer. And again, Q equals MC delta T. And one thing to notice or note is that our T will be the same value because it's still all part of the same system. The first thing I'm going to do is just calculate the temperature change. So we have 31.9 minus 21.4, so 10.5 degrees Celsius. Okay, so let's start with our solution. Our solution here, it looks like we have a solution made up of two things. So we have our NaOH and we have our HCl. Now this mass includes the cup, so we know that the cup is 4.5 grams, so the HCl is equal to 100 grams. So by adding both of these together, our total solution will be 104. Oh, sorry, that's 54. This should be 150. 150. So our total solution should be 154 grams. Our specific heat capacity that we're given is that of water. This level we're usually assuming it's always water. And then our temperature change of 10.5. Those stay the same. So now these are going to cancel out. We're going to be left with the joules. So we're going to be left with, hold on, I need to just move this down. And we're going to be left with 154 times 4.184 times 10.5. We're going to be left with 6,076.5 joules. That's just part one. So this is one part of our surroundings. Then we're going to find each part and add them all up together. Okay. And so now we're just going to do it for the same cup and thermometer. So the easier part about this is that we don't have to add up any masses because there's only one mass of the cup, and that is 4.5 grams. Our C is, oh my gosh, 1.30 joules per GC. And then our temperature change is, of So we have 4.5, 1.3, 10.5, and we end up with 61.425 joules, which seems low, but it's also the cup, so makes sense. Okay, the last one is the thermometer, so I think we have 12 grams of thermometer. We have a 0.84 heat capacity, same temperature change again, 10.5 Celsius, and again to do this 0.84, 10.5, we get 105.84. So now we can add all of these up in order to create the surroundings. So this is plus 61.425 and plus 67.65. So our Q surroundings is going to be equal to 6932.364, and that's in joules. Okay, so now we are not done. We have just found the heat of the surroundings. In order to find the heat of the system, we need to do our fun equation over N. Okay, and this is molar enthalpy. It does say just to find the enthalpy of the system, which brings me maybe to my next problem. What I want to search up here. So let's just see. Okay. So even though it's okay. So this is the enthalpy of the system, but so this is the enthalpy, or the enthalpy of the system, sorry, is not positive, it's negative, but it's 60, so we can do this divided by 1000 is 6.9 kilojoules, negative 6.9 kilojoules. That is the enthalpy of the system. But so enthalpy, okay, that's the enthalpy of the system, but this is going to find our molar enthalpy, which, okay, I just get confused sometimes when, like, do I find molar enthalpy or just enthalpy? But okay, this time we're gonna do molar enthalpy, even though it says find enthalpy of the system. We'll say in kJ per mole. Okay, that makes it more clear. So now we have moles, we have the system, okay, and now we have two possibilities of moles that we can use, right? We have HCl and we have NaOH, so HCl and then we have NaOH. We need to determine which one is the limiting reactant, so let's do exactly that. HCl is 150 grams over right 36.46. So we're gonna get 36.46, 4.11 mole of HCl. This is 4 grams over plus 16 plus 1.01 over 40. So we get 0.1 NaOH. Obviously these are in different units, so we need to determine which one. NaOH and HCl, oh, okay. It's a 1-to-1 ratio, so it's gonna be the same thing. We're gonna multiply it by 1 mole NaOH over 1 mole HCl. Same thing though. So this is our limiting reactant. This is the N we use. So our N is going to be, enthalpy, sorry, is going to be negative 6.9 kilojoules over 0.1 moles. So we have negative 6.9 divided by 0.1. We get equal to negative 69 kilojoules per mole, which would be right, except I definitely forgot to carry some significant figures. So let's just see if I can figure this out here. Okay. Our N value is 0.1 though. Right, we have 4.0. 0.1. It's not even, it's 1. Okay, I'm gonna go through the sig figs. Okay. Okay, so it is 3 sig figs. But why? Because the temperature is 3 sig figs. So the significant figures for multiplication and division result same number as the least. Okay. So 3. Okay. So we have 3, 3, 3. So it should be 3. And then addition is based on decimal places. So I don't understand the addition and subtraction part. Where we have, okay, so we have, I think, okay. Least number of digits after the decimal point. Digits. So it's going to be 1. Okay. Oh, okay. So in this one, I think our least was 2. What? Hold on, I think I did it wrong. So 154 times 4.184 times 10.5. Okay, that gives us 3. So we have 3. Oops. We have, I think, 3 here as well. And we have 2 here, I think, but let's just confirm. 0.84 times 10.5. We have 2. So for adding and subtracting, we should have 2 here. So that leaves us with 6,932.36. Divided by, and this is where we go, 0.1. Wait, no. Man, I don't know. Okay, I'm very confused. I can't lie, like, this is what's gonna get me my marks taken off, but okay, I'm gonna go figure that out. Okay, thank you for watching. This helped me quite a bit. I hope it helped you either sleep or maybe sleep and study. I think I'm gonna go do some more review because I need to. But yeah, thank you for watching if you watched it this far, and have a good night.